The thing about AI, it can take into account thousands and thousands of tiny data points, like at what time in the day you came in to ask for a loan. And it has a 0.07% influence on the decision, but it's there.
Right.
Sometimes people say, okay, even when computers will make the decisions, we'll have a law, like in Europe with the GDPR, that it has to be explained. Like humans have the right for an explanation. If you applied for a loan, the bank said no, you have the right to get an explanation why the bank said no. But this is completely irrelevant because the bank will say, well, we have this algorithm and the algorithm went over masses of data. If you want, we can print you all the data, but we can't make sense of it.
It's no question that AI has transformed our lives drastically. Every day, more and more decisions are being made by AI. As these decisions grow in importance, we need to find a way to interpret the decisions that are being made by this AI. Conventional deep learning models has made interpreting the decisions tough. So, we need another way to associate the inference process of this model. In this project, we propose a parallel architecture named the Fuzzy Embedded Recurrent Neural Network. The recurrent neural network and the fuzzy system shares the same input and output linguistic. With this, we are able to model the inference process within the recurrent neural network. By observing the fired rules, we're able to interpret the inference process of the recurrent neural network. But what are fuzzy rules? Fuzzy rules are simple if-then rules that explain that if we meet the conditions of the rule, then the output of the system will be the consequence of the rule. Training of the FERNN takes part in 3 steps. Firstly, we perform fuzzification on the training data. Then, we take the fuzzy input values and output values and feed them as training data for the deep structure. Then, we use that to generate the rule base. Each rule in the rule base consists of the conditions, the consequent, and a pseudo-weight, where the pseudo-weight represents the weightage or the importance of the rule within the learning system. Using the FERNN to make predictions requires 3 to 4 steps. Firstly, we perform fuzzification of the input data. Then we feed the fuzzified input data to the RNN. Then we perform center of area defuzzification to convert membership values to CRISP values. The CRISP values will be our final output data. Finally, we can inspect the fired rules to interpret the decision made by the system. So we develop a visualization tool to inspect the rules that are being fired. As you can see here, each of the colors represent each of the different inputs being fed to the FERNN system. For each of the input, they also have a different degree of intensity for the colors being represented. These intensities represent its relative value in the membership function. The intensity of the rule nodes represent the pseudo-weights of the rules in the system. As we use Hebbian weights, recently activated rules have higher weights, while distant rules have lower weights. Through this tool, we're able to inspect which are the nodes that are being activated within the RNN and which are the rule nodes that are being applied. Finally, we also use the FERNN as a price predictor to forecast up to 7 days of future pricing data. We incorporate the prices into a FMACDH strategy, and we use genetic algorithms to optimize the parameters that are being used in the strategy. In this strategy, we use exponential moving averages as the base indicator to reduce the time lag of the moving average. However, the exponential moving average still lags behind the true moving average. So, we use our forecasted prices to attempt to reduce the time lag of the moving averages. However, as we predict further into the future, our model might not be as accurate as it is if we were to predict just only 1 day ahead. So, we assign exponentially lower weights to predictions that are further into the future. For trading, we have selected 4 different ETFs of various risk index. Firstly, we have the SPY, which is the ETF that tracks the S&P 500. Next, we have the VGK. The VGK is an ETF that tracks the FTSE Developed Europe All Cap Index. Next, we have the VWO. The VWO is an ETF that tracks the FTSE Emerging Markets All Cap China A Inclusion Index. Lastly, we have the AGG. The AGG is an ETF that tracks the total US investment grade bond market. We trade these ETFs from January 2011 to January 2021. Our strategy has enabled us to outperform the buy and hold strategy. Our forecasted results has also helped us in identifying the peak and troughs of the price actions. In conclusion, we're able to reap the benefits of both fuzzy systems and the deep structures. We also visualize the activations within the FERNN and use the FERNN as a price prediction within our trading strategy. Future works can explore the tagging between rule nodes and the nodes within the recurrent neural network, and also experiment with using other trading strategies.